Okay, B1 torque problems continued. Number 1, a rigid bar with a mass M and length L is free to rotate about a frictionless hinge at a wall. The bar has a moment of inertia, I equals 1/3 ml squared, about the hinge and is released from rest when it is in a horizontal position as shown. What is the instantaneous angular acceleration when the bar has swung down so that it makes an angle of 30 degrees to the vertical? So the reason the bar swings is because there's force of gravity. There is the force of gravity acting on the bar, so it causes it to swing down. Now, the force of gravity acts at a point that is at the very center of the massive object. And if the bar has length L, then this force of gravity acts a distance of L/2 from the hinge. And remember, whenever we have torque equals F(r) sine theta, where F is the force, R is the distance the force is applied from the axis of rotation, and theta is the angle between the force applied and the moment arm, which is this distance, this R from the axis of rotation. So only the perpendicular component of a force gives rise to torque. So only the perpendicular component of this force of gravity causes a torque. In this case, I have that's 60 degrees, 30 degrees. So I'm going to use the angle 30 degrees. I can show you here. This is also 30 in here. And the perpendicular component of this moment arm is Fg sine 30 for this part right here. And torque also equals I times alpha. So I can set torque equal to torque. That's always the steps in these equations, where the force applied is the force of gravity, m times little g, times L/2 for r, times sine of 30 degrees, and I set that equal to 1/3 ml squared times alpha, and I can solve for alpha. Sine 30 degrees is 1/2, sine 30, let me double check, I can't remember now. Sine 30 degrees, yeah, 1/2. So m little g times L/4 equals 1/3 m L squared times alpha, and then I'll just solve for alpha. You see my m's cancel, multiply by 3 on both sides, and you can finish the rest. Number 2, a 3 kilogram Academy sign is hung from a 1 kilogram 4 meter horizontal pole as shown. The sign is hung 1 meter from the right side. A wire is attached to prevent the sign from rotating, and we're looking for the tension in the wire. So solving for tension. Okay, so this system is in rotational equilibrium. So this tension provides a torque. It tries to rotate the pole upwards. Meanwhile, the pole has a force, its own force of gravity, and the force of gravity of the sign, the weight of the sign, and I'll actually call this the weight of the pole, are trying to rotate this system down. They're in rotational equilibrium, so I can say the torque of the wire equals the torque of the pole plus the torque applied by the sign. Now I'm going to plug in for this equation. I'll start with the wire. Please remember that it's only the perpendicular component of this tension that gives rise to torque. Only this component of the tension that is at a 90-degree angle with respect to the moment arm. And it acts all the way at the very end of the pole, a distance of 4 meters from the pivot point. This is the pivot, or the axis of rotation, and this is where this force is applied. So I can see this is an angle of 30 degrees. So the force applied by the wire is T, the tension, times sine of 30, times the distance from the pivot point is 4 meters. That's the length of the pole. and then I set that equal to the torque of the pole that's caused by the pole's own gravitational force. The pole has a mass of 1 kilogram times, I'm going to use the gravitational acceleration of 10 meters per second squared, times how far the force of gravity acts. Remember, the force of gravity affects an object's center of mass, and that is 1/2 the length of the pole times 2 meters, plus, okay, so again, this gives me my force, and this gives me my R value, the distance to the moment arm. In this case, the force of gravity is at a 90-degree angle. Sine of 90 is 1. Plus the torque caused by the sine, so it's the weight of the sine. This is a distance of 3 meters. If it's 1 meter from the end, then it's 3 meters from the pivot point. Okay. The weight of the sine is 3 for the mass times 10 for the gravitational acceleration times a distance of 3 meters from the pivot, and then I can add these two sides up. I can divide away the sine 30 times 4 meters and solve for t. So at this point you should be able to get the tension, which is what we're looking for. Question number 3, what is the angular acceleration experienced by a uniform solid disk of mass 2 kilograms and radius 0.1 meters when a net torque of 10 Newton meters is applied? The disk spins about its center. So this has a radius of 0.1 meters, is rotating because this net torque of 10 Newton meters is applied. So the equation I'm going to use that involves angular acceleration, which is what we're solving for, is I times alpha. And you can use your data booklet to solve for the moment of inertia. That's what you'll need to do anytime you're not given an equation. From the data booklet, it says I is sigma, the sum of all of these masses that are distributed at some distance from the axis of rotation. In this case, I just have one massive distribution. It's the 2 kilogram mass times the moment arm. So this 2 kilograms is distributed evenly throughout this disk at a distance of 0.1 meters squared times my unknown alpha, and I can set this equal to 10 Newton meters. Solve for alpha, and remember alpha has units of radians per second squared. Okay, question number 4 of 5. A light string attached to a mass m is wrapped around a pulley of mass m sub p and radius r. If the rotational inertia of the pulley is 1/2 mpr squared, derive an expression for the acceleration of the mass. This is such a common question in IB that you're just going to have to memorize how to do this and study and practice doing this one over and over. So here we go. The object is going to accelerate. This block is going to accelerate to the floor. It accelerates less than g because there is tension pulling back up. So you start by analyzing the linear forces. This tension is what causes torque. So tension is the force that causes torque here. In this case, it causes torque on the pulley. So the pulley is going to rotate down as this block descends to the ground. And ultimately there is a net force, F net, of the block. And so I'm looking for the acceleration, the linear acceleration of this mass, m. So I know that F net equals, I build my linear net force equation, Fg minus tension. Tension will never be given, so it's unknown. I'm going to have to solve for it, but just remember Newton's second law. F net is m times a equals m times g minus t. So okay, I have two unknowns in the equation. I'm looking for acceleration, but tension is unknown. So let's look at torque. Let's look at what's going on in this situation. In this case, I have a pulley and it's rotating, which means that there is a torque acting on it. Torque is F r sine theta, F cross r. The r is the radius of the pulley, so I'm just going to redraw this radius here. And the tension is at a 90-degree angle. The tension is this linear force that causes the rotation. So I'm going to plug in for F, I have tension. R is this capital R, and sine of 90 degrees is 1. So we're getting maximum torque. Okay, I still can't do anything with this because I can say, okay, torque is tau over R. I'm sorry, tension is torque divided by R, but that doesn't help me because still torque is unknown. So there's one more equation for torque. Always you're going to use 2 equations for torque unless it's something easy, like number 3, unless they give you the torque. So I also have to relate my other equation, which is I times alpha. Alpha is unknown, but alpha is related to the linear acceleration of the system because alpha equals linear acceleration over r. If you don't know this, you need to put this in your data booklet. So now, like before, I'm going to set these two values equal to each other. Tension times R equals I times A over R. Okay, so tension equals I times linear A over R squared. And I can just plug this in for my tension down here. So when I do that, I get M times A equals M times G minus I times linear A over R squared. Now I have an expression for I, and I can plug in 1/2 M sub P R squared. So M times A, you bring any term that has A, you bring it over to the same side of the equation because then we can factor out later. M times A plus 1/2 M sub P R squared, this is my I, so I just plugged in for that and I've added this over to one side, times A over R squared equals M times G. My R squareds cancel. I'm going to factor out A. So I have A times, open parentheses, M plus 1/2 M sub P equals M times G. And I can divide both sides by the expression M plus 1/2 M sub P. And I get, for my final answer, linear acceleration is M times G divided by M plus 1/2 M sub P. And that's it. And finally, we have this question number 5. Find the speed of a disk of radius 0.5 meters and mass 2 kilograms at the base of the incline. The disk starts at rest and rolls down the incline with a height of 5 meters without slipping. The static friction coefficient is 0.25. The incline makes a 20-degree angle above the horizontal. So we're going to need to get the linear acceleration. Some very important piece of information. If you're given the static friction coefficient, you are cool to proceed. You don't need to analyze the linear forces because for rolling without slipping, only the force of friction causes rotation. Only the force of friction causes rotation. If the force down caused the rotation, or caused the object to move, then the object wouldn't roll, it would slide. So only the force of friction acts to cause this thing to roll. So because we're given the force of friction, because we're given the static friction coefficient, we don't have to do much with this. So I need to get an expression for linear acceleration, and we're going to again use our torque equations. Torque is I times alpha, and torque equals F times R times sine theta. FR sine theta is the same thing as the cross product, where this force is the force of friction, so I'll say F sub F times R is the radius, and the force of friction is at a 90-degree angle with respect to the moment arm. So F sub F times R, and this is torque, and I'll set it equal to the other equation for torque and replace this alpha. Alpha equals linear A over R, so replace it, linear A over R. Okay, so now I need to just plug in and I can solve for linear acceleration. Once I get linear acceleration, it's just a kinematics problem. So the force of friction is mu times the normal force times R equals I. Again, if you're not given an equation for I, just use the equation from the data booklet. That's mr squared times linear A over r. So you see all of my r's cancel out, and I have mu times the normal force equals m times A. So let me plug in now for my normal force. Analyze your forces on an incline. The normal force in this case, this is 20 degrees, it is mu times m times g times cosine of 20 degrees equals m times A. My masses cancel, so mu is simply, A then is mu times g times cosine of 20 degrees. And you can solve for the linear acceleration. Then to get the time it takes, what am I looking for? Oh, to get the speed of the disk at the base of the incline, we're looking for the final velocity. Initial velocity equals 0. Final velocity is what we're solving for. You have acceleration. One more piece of information you need to solve this kinematics problem is displacement. This is a 20-degree incline, and the height of the incline is 5 meters. You're looking for a hypotenuse given a side opposite to the angle. So your displacement then will be 5 meters divided by sine of 20 degrees. Once you have that, you can easily solve for the final velocity. You can use the equation v squared equals u squared plus 2as. I hope you found this video helpful. Use this as a guide and study, and thanks for watching.